Right, we are going to take a look at our notes for angle, side, angle, and side, angle, side. They're the name for two proofs for us to use in order to prove two triangles congruent. We have three new properties that we're going to look at here. Two of those properties literally share a name with the phrases I just said, but you might notice also have an abbreviation in the heading that you're going to see me use. But there is a third one called reflexive property, which is going to kind of seem silly to say, but we're going to be using it as part of a checklist of three things we're trying to achieve in order to prove that two entire triangles are congruent. So in a checklist of proving triangles are congruent, which hopefully you might be able to see from this picture, which I've drawn to scale, that we have two equal size or congruent triangles here, we're going to be able to prove that everything about these triangles is congruent if we can prove three specific things. Either that two sides and an angle in between them are congruent, or that two angles which share a side between them are congruent. If we can prove either these three things or these three things, it ends up that the entire triangles are guaranteed to be congruent. Reflexive property, any measure that is equal to itself, might end up coming up in this situation from time to time because maybe the way that the triangles are drawn, they could share literally the same side or angle and get one of these things ticked off of our checklist. So what I'd like us to do is to just dive in and lead by example. You can see in this first example, we're going to try to prove that triangle DGA is congruent to triangle EFA. And so if this left triangle basically is the same as this right triangle. We're going to prove that for this specific scenario, where we know DG is equal to EF. So I'll go ahead and do some little congruency markings to show that they're the same. A is the midpoint of GF. So A is the middle point of GF or GAF. And that DG is perpendicular to GF. And EF is perpendicular to GF. So let's get those last two on our statement and reason chart and marked in the picture. So the first thing outside of the givens that it yields us is from this midpoint. We're going to go ahead and use the definition of midpoint to go ahead and note that that means GF was cut perfectly in half, like a segment bisector also does. So we are now allowed to say that AG is congruent to AF. And so what you'll notice is in my picture, right now I have two sets of congruency markings. And if these are the ones that we're learning today to prove two triangles congruent, we now know which one we're going to look at. We're going to look at side, angle, side congruency here because I have two sides, not two angles proven so far. So my hope is I can get the angle between each of these pairs of sides congruent. And it just so happens that our other set of givens do that for us. DG is perpendicular to GF. So DG comes down and makes a right angle or a 90-degree angle there. And EF is perpendicular to GF. So it's coming down, forming another right 90-degree angle there. And so we have two ways that we can go about doing this. We could say something along the lines that these two angles are both right angles, and we know that right means the same no matter what. Or alternatively, what we can do is we could say something like angle DGA is equal to 90 degrees. But we also, for the same reason, are going to know that angle EFA is also equal to 90 degrees. And that would be because perpendicular lines form 90-degree angles. But because both of these share something in common, that's going to allow us to say they're equal to each other. And we know they're equal to each other because of the transitive property. And so we now have a set of sides, a second set of sides, and an angle between them. Side, angle, side. We've done three things off of a checklist, and now this definition activates. Given a one-to-one correspondence, in other words, this one corresponds to this one, this double mark corresponds to this double mark, this right angle corresponds to this right angle. If two sides and the included angle of a first triangle are congruent to the corresponding sides of the second triangle, then the correspondence is congruence, aka the entire triangles have all their parts line up with one another. And so that allows us to say that D corresponds to E, just like G corresponds to F, and A is corresponding to itself. And we can say triangle DGA as a whole is congruent to triangle EFA as a whole. And our reason is this side angle side, or SAS congruence. Okay, we're going to see this works for a different set of three things. It's the same definition, basically. If you compare them, it's just two sets of angles and the side between them. So let's flip our paper to the next page and the next example so we can take a look at one like that. Okay, so what we have here is that we have a given that BD is an altitude of triangle ABC. What we might remember is altitudes are also known as height, but we measure height perpendicular to an opposite side or a base. So we now have established already that we have a set of right angles here. So I'm going to go ahead and call them 1 and 2. And before I forget it, I'm just going to look at only that given so far and get something written down right away. So angle 1 is equal to 90 degrees. Angle 2 is equal to 90 degrees because perpendicular lines form 90-degree angles. And with a transitive property after that, I now can say that those are equal to each other. And so for angle side angle congruence, one of our things is now checked off the list. If we look at the next given statement, the only other given, BD bisects angle ABC. So up here, that large angle ABC has been cut perfectly in half. Let's go ahead and call those angles 3 and 4 just to make it easier to write about them. And we can now say angle 3 is equal to angle 4. And that's because of the definition of an angle bisector. And we're out of givens. But I don't have 3 sets of things. I have a set of angles for my first item. I have a set of angles for my second item. I need a third item for angle side angle. But it has to be the side between them. So what you should notice is our first definition from the front is going to come into play. We can say, because of what's known as the reflexive property, it's reflecting on itself. Where you look in a mirror, you see yourself. Something is equal to itself. And so in the triangles that I'm asked to prove in this example, I need triangle BAD and triangle BCD. You'll notice BD is in both of them. That also happens to be the side between the two sets of angles that we have. So because it's the same, it's automatically equal to itself. The way we mark that in a diagram is X marks the spot. It's almost like we're doing a congruency mark both ways for both sides or both triangles, left versus right in this case. So we're able to automatically say that the line segment BD is equal to the line segment BD. I know standalone, it's common sense that it equals itself, but we're saying it because it's the third thing we needed for a congruence. This is the reflexive property, just to say that one more time. And now we're done. We have a set of angles in 1 and 2 being equal. We have a side coming off of that angle, that's reflexive. And we have another angle there that side was connecting to, another angle pair. So we're going to have angle side angle congruence here for the two triangles mentioned. Now, you should make a note that when I've been naming these triangles so far, I've been naming their corresponding parts. In other words, B is where angles 3 and 4, two congruent angles, started. It then, in name, goes to A and C, two angles that end up being congruent but that I didn't talk about. And then they both end going to angle centered at D, which were both of our right angles. So it's the two single marked angles, then in name the two unmarked angles, and then in name the two right angles. And so we will name the triangles with their corresponding spots lining up every single time. And now this proof is complete. We have proven that this triangle on the left, BAD, and this triangle on the right, BCD, are congruent to each other. All right, we have one more that we're going to look at for our notes today. You might maybe want to try it on your own for a few moments. It's not a bad idea. Pause the video and maybe come back to this. But let's get into it if you didn't pause or if you're joining us again. So, LN is the perpendicular bisector of MO. So I see the word perpendicular there. It's in my givens that I copied down. So if that's the perpendicular bisector, that means perpendicular, we have those right angles forming. And so maybe I'll show you the alternative way to say this that I mentioned earlier, but that we didn't actually write down. I'll call these angles 1 and 2, and I can say angle 1 and angle 2 are right angles. And the reason is perpendicular lines form right angles. And then, because that specifically means a single answer, 90 degrees, that's what that word means, we know all right angles are the same measurement. All right angles are congruent. That allows us to know angle 1 is congruent to angle 2. And so I have those there. You could have still done what we did in the other two examples. Say that they're 90 degrees and then use a transitive property. We're also told that we have a bisector here. This is a bisector of MO, not angle MLO. It's a bisector of MO. It is a segment bisector. So I know those two are congruent to each other. Those two being MN and ON. Those two line segments are equal. The definition of a segment bisector. And once again, we have a side and an angle. So maybe I could get these angles congruent, but I'm out of givens. Or I could get this side congruent to, itself, that same side. So this ends up being a reflexive property, producing a side, angle, side situation. So step 5 is going to be LN is equal to itself or congruent to itself because of the reflexive property. And we are now going to be able to almost be completely done. I ignored the fact that this wasn't asking us to prove triangles congruent. Instead, it asked us to do something a little bit different. But in order to do that, we're still using these definitions from earlier, meaning the correspondence is a congruence. So if I can prove that the two triangles are congruent, I now know all of their parts are congruent. So I'm going to now say that triangle LMN is congruent to triangle LON because of the side angle side congruence. But this is where if you try this on your own, you might not have known how to finish up or how to get here, because there is a 7th and final step. It is the fact that now that I have the triangles congruent, the other sides and angles that I haven't yet mentioned are all going to also be congruent. So we have the other two sets of angles congruent to each other correspondingly, and the third side that was not mentioned in either of them are also congruent. So that means these sides that I didn't yet use, but are part of both of these triangles, they're congruent. LM is congruent to LO. And here's how we say that. And this is an abbreviation that I want you to write down and learn. You're going to use it all year long for a lot of things. It's called CPCTC, which is an abbreviation for corresponding parts of congruent triangles are congruent. So if I look at how I named the triangles, LM, N, LO, N, the LM and the LO were corresponding parts. So those corresponding parts of the congruent triangles I just proved, they independently themselves are congruent. Okay, what you should be able to do at this point is to go back, re-listen to anything I said for these three problems, maybe take them a little bit slower if you want to re-watch them. But once you feel comfortable, what you can do is move on, okay, to our homework, which is on the back page. Okay, because I am not there, these soft cover geometry textbooks, the ones that you took home by Isidore Dressler, you don't necessarily have to go to these pages. I should have them printed out, and I'm giving them to you, those questions. But I'm also going to ask that you try and go ahead and do this construction. Don't worry too much about it. I'm more focused on you worrying about these examples, which are based on side angle side and angle side angle. Thank you.